John has over 30 years of experience specializing in major rail, tunnel, subway, and urban infrastructure projects, and has led many multidisciplinary teams all around the world, from London to New York and Copenhagen to Bangkok. So we're excited to hear your views around digital fabrication and UK infrastructure. John, the floor is yours.
Thank you. Good evening, good morning. Can everyone see the picture? So, digital fabrication is not yet the new normal in infrastructure, but what enables it? And how do we meet the challenges of logistics and labour shortage and operational continuity and cost control? Owners and operators need maximum reliability, minimum maintenance, operational safety and continuity. And to tackle these problems, we feel that we need a multidisciplinary approach, some exploration, some collaboration. So as an example, Arup and Costain began a conversation last year about opportunity to do this in the rail sector. We focused on rail tunnel system fit-outs. We looked at the Crossrail project experience for lessons on where to go next. So in the slide, you see some recently built Crossrail tunnels. The rail systems supported on brackets drilled into the concrete, some manually, some by automated machine. On the left, galvanized steel walkways with adjustable struts that could be installed early and flipped out of the way for the track work installation to suit the sequence and program constraints in the tunnel. So we considered how these tunnel walkway designs have evolved from the solid mass concrete of the UK's High Speed 1 project. It's on the left. That's delivered in 2005. That's simple, but with a lot of embodied carbon. Through Crossrail in London, designed 2012, built around 2016, with a number of adjustments to the design from the client and engineer, the reference design. And these were done to address tolerance and logistics issues, solving some problems, but actually raising others. We know that in a typical tunnel, or let's take the High Speed 2 high speed rail in the UK project tunnels now in design, about 2/3 of the embodied carbon is in the concrete, and that's after cement replacement measures. And 10% of that's in the walkways, if we do them in solid mass concrete the traditional way. And the thousands of brackets and fixings along the tunnels are a critical path in programme, and they have to be built working in the constrained environment of the tunnels, where, for instance, long objects cannot be turned round. Obvious if you think about it, but a serious issue. So what if point cloud scans of the as-built tunnel joints in the segments and of the geometry of the thing as built are made, and the point cloud transferred to BIM, giving precise locations and a geometry in space, so that now we can calculate how to avoid no-drill zones, joints, and we can allow automated calculation of each bracket dimension ready for 3D printing. On-site cutting and adjustment is minimized, and no spare parts inventory is needed, just a 3D printer and the details of what we built first time. Capital costs in the confined environment of the tunnel are dominated by logistics and programme. So we're continuing to explore these possibilities together with Costain. From there to there, from there to there. So, apart from the rail sector, what can we see coming? Well, there's a number of signposts here. I've picked a couple of where the digital future may be. For instance, on the left, a 3D printed footbridge made of stainless steel. It was printed by MX3D, our collaborators. It's now certified for public use in Holland. And that gives the green light, that gives the green light of regulatory approval to the whole idea of 3D printing and using, in this case, stainless steel. On the right, a printed drainage chamber. This is in France and it was printed by X-Tree. It's made to measure for the existing pipes and underground obstructions, so it allows installation with minimum road closure time. Now, how vital that is, we can soon see if we think of the operationally critical situations it could be in, like a major road or even an aircraft runway. So here, operational continuity is the driver, not the cost of the printing or the object. In the marine sector, we're exploring the use of 3D printed concrete or similar materials to create a biodiverse artificial reef. The example in the lower part of the slide from Monaco and the finished product bottom right, in use by the fish, features 3D printing by D-shape. Objects up to about 4 meters in dimension can be printed at present. This opportunity is not just about biodiversity, but also about ecotourism projects in damaged environments. This starts to change our thinking away from the traditional use of the concrete blocks simply for wave energy absorption. So let's consider the generic factors for infrastructure as we try to move from today's solution to tomorrow's. We need teams who can solve materials and safety problems. We need to consider market and procurement factors, and that includes the issues of labour shortage now and even more in the future. We need to optimize logistics and program, because many times in the infrastructure sector, that's the driver. And we need to develop digital tools to turn survey into fabrication, as with that idea to turn a point cloud of as-built tunnel survey into a BIM model for fabrication. And if we step back further and look at sector opportunity, we think their greatest potential for digital fabrication in infrastructure may be in the water and energy sectors. Rail, bridges, roads, yes, but less so maybe because of the regulatory environments and the industry cultures. In infrastructure, digital is about reliability rather than excitement, continuity rather than geometry. But the opportunities are all there to apply digital thinking and fabrication to address the skills shortages to keep critical structure operational. So where does your project sit? Talk to us afterwards about the opportunities to work together. We look forward to the discussion. Thank you.
Thanks, John. Quite a different challenge there you presented to, I think, what Tristram showed.